Good evening, sir.
Yeah, good evening. Am I audible?
Yes, sir.
So maybe we'll start the class today. All right. So in the last class, we were discussing about unconstrained optimization. So first we discussed about what was optimization. Then we discussed univariate optimization problems. And finally, we moved to multivariate optimization problem. So in the common way to solve the unconstrained optimization problem was to find the two derivatives. That is the first derivative, which in case of univariate is a single derivative, whereas in case of multivariate, we usually find the Jacobian, and we equate that to zero to find the optimum points. So it can be maxima, minima, or saddle points, depending on um, the nature of the Hessian. That is the second derivative. Like if it is positive definite, we will say that the optimum point that we found out was the minima point, or if it is negative definite, or if it is not positive definite, or if it has negative eigenvalues, we can say that it is maxima point, or if it is zero, then it is a saddle point. Then we discussed a lot of problems with respect to that topic. Then we moved on to gradient descent method. So which is a method that is applied in backpropagation algorithm to find the or tune the neural networks. So in that we found how the points are updated. Like if we had xk plus 1 is the new point which we send step from the existing point xk plus we have a step length and the direction. So sk is the direction which is the negative of the gradient of the function, because the gradient of the function always denotes, or the direction it shows is the where the function increases, whereas in the gradient descent method we want to move towards the minima point, so we will take the negative of the gradient as the direction. Well, then we saw how the learning rate affects the convergence, how high learning rate is sometimes better, and how it can cause oscillations, or how a smaller learning rate will take a lot of steps to converge. And we had discussed some problems related to gradient descent methods. So in today's class, we will be focusing on constraint optimization. Right. So what is the main difference between constrained and unconstrained optimization? So in unconstrained optimization, that is in the last week, uh, the functions that we examined, or in all the problems that we were looking at, we didn't give any limit where our search has to be bounded. That is, there were no boundaries, or the boundaries were soft in the sense like mm, we were not taking infinity or minus infinity as a value, but there was no restrictions as such. Whereas in case of constraint optimization, we will be examining the functions with constraints. That is, so if this was the unconstrained problem, so if we were to find the maximum in this case, so these points can be the maximum values. Whereas once we constrain our boundary to this region, the maximum limit is up to the points inside the boundary. So a constraint is a hard limit placed on the value of a variable. So if you have f of x, so this x can take only values within this interval. Whereas in here the x was, there was no boundary or constraints to the x. X can take any values. So what problems it can cause? So let's say let's take the gradient descent itself. So let our function be like this. Yeah, so if this was the boundary that we have set, and so this is the active area now. And if we start from here, so if we start from this point, we cannot move towards the descent direction because there is a constraint to our problem. So we'll see how these constraints, the problems with constraints can be solved with examples. So one practical example that we can see now is this. So what we need to do is we want to travel from Surat to Mumbai. So that is our aim to travel. But even though that is the aim in the first case, in the second case, we are putting a constraint, like we have to visit the Nashik city on our way to Mumbai. So if we are to take this route, we cannot meet the constraint. Whereas if the constraint has to be satisfied, we have to change our route so that the route becomes longer. In sense of optimization, like if our problem was just to reach Mumbai from Surat, this is not the optimum path. The constraint path is not the optimum path. Whereas in our actual case, since there is a constraint, we have to move via Nashik towards Mumbai. So that is the restriction, the constraints imposed on the problem. Now looking at another problem. The task is to climb as high as possible on the mountain to have a better view of the moon. So on a mountain, we have to reach at the highest point. So there is always a possibility to walk straight up, but it's not always the best route to reach the topmost point. And here we are putting a constraint as well. That is, the car must be on the road. So in all the guard sections, we never see the roads to be placed directly, like going in a single ascent. We'll be taking lot of turns, hairpins and all to reach the top points. Now let us move towards the mathematical side of the constraint optimization. So first we will start with equality constraints. So the equality constraints optimization are such problems where the constraints will have an equality sign, or the points or the restriction is such that the optimal point will lie on the constraints. So here if you see, the black line is the line represented by 3x1 plus 2x2 is equal to 12. Whereas the circles represents the contours of the function. So if you put x1 equal to 0 and x2 equal to 0, we get the function 2x1 square. So let's say this is f of x. So if you write f of x, then x1 So f of x, x1 and x2. So if x1 and x2 is equal to 0, then f of x is also equal to 0. So if it was an unconstrained problem, we know that this is the optimal point. That is denoted by the red star, which is x1 is equal to 0 and x2 is equal to 0. But the problem here is, since you have a constraint, this 0, 0 point does not lie on the black line shown here. So this is not a solution for our problem. So graphically, if you see, if we move away or if we follow the line, so any point on this line satisfies our constraint. But we have to find that point on the line which will give the minimum. Okay, somebody asked a question. Prajakta, do you have some question? Okay. So now our aim is not just to satisfy the condition like what we have done in the earlier class. So in the earlier class, what we have done is we have to just find the two derivatives, that is dou by dou x1 of x, that will be equal to 4x1. Then we have dou f by dou x2, which will be equal to 8x2. And we have to equate both to 0, which gives the solution x1 equal to 0 and x2 equal to 0. So that is not what we want right now, right? Because we have a constraint as well. So one method is to solve these problems graphically, but it's also difficult, whereas because our constraint or our functions are higher order functions, and our constraint is a linear constraint. So how we can solve such problems, that we will see today. So in this graph, if you see, the function values increases in this direction. So this one has having lesser value compared to this circle. So the point at which this constraint is tangent towards this curve, that will be the minimum point of the solution of our constraint optimization problem. So now we introduce some technical terms. So first one is the Lagrange multiplier. So this Lagrange multiplier is a technique used in optimization problems that involves constraints. So it actually combines the constraints and the function to get a single equation, so that we can use our techniques like derivatives and all to find the solution. So this Lagrange multiplier helps us to find the optimal solution of an objective function while satisfying one or more constraints. So let's say our constraint is denoted by the equation gxy. Then we can write so the objective function, we have f of xy, where this is a multivariate problem. Then we can write derivative of f of xy is equal to minus lambda into derivative of g of xy. So this lambda is called the Lagrange multiplier. So let us first solve a problem, and let's see how we can find the solution in our problem which we have already seen. So now first what we have to do is we have to find the Lagrange multiplier. So what was our equation? So we had delta f of x is equal to minus lambda delta f of xy. Okay, sorry, x1 x2 or something. So and g of x1 x2. So now what we have to find, we have to take the derivatives. So what we have to do, we have multiple variable. So it will be 4x1 and 8x2. That will be equal to minus lambda. Similarly, we have to take the derivative of our g function or the constraint function. That will be equal to 3 and 2. So now what we get? We get 4x1 is equal to minus 3 lambda and 8x2 is equal to minus 2 lambda. And we also have the constraint, that is 3x1 plus 2x2 is equal to 12. So we have, mm, let's say how many equations we have. So we have three equations and three unknowns. So we have x1, x2 and lambda. So these are the three unknowns that we have, and we have three equations. Now just we have to solve these equations. So maybe we can simplify this a bit. So let's try to convert everything into one single variable. All right. So with from these two equations, we can write it as 2x2 by x1 will be equal to 2 by 3. So it will be almost 2 get cancelled. So we get 3x2 is equal to x1. Now let us substitute x1 into this equation. So what we get is 9x2 plus 2x2 equal to 12. So x2 will be approximately equal to 12 by 11. Now we can find the x1 also. So x1 will be 36 by 11. So x1 will be equal to 36 by 11. Now let us see if this satisfies our equations. So we have 3 into 36 by 11 plus 2 into 12 by 11. So what will be it? So that will be 3 plus 3 into 3, 9 plus. So it will be 11 into 12 by 11. So that is equal to 12. So it exactly satisfies our constraint. So our solution is x1, x2 is nothing but 36 by 11 and 12 by 11. Now, if we put these two values in our function, we get the minima of the function with the constraints 3x1 plus 2x2 equal to 12. All right. So now we have one more problem. So if you want to try, you can try, or we will solve this one also. Maybe you can try for 5 minutes. After that, we'll discuss the solution. The first thing is you have to formulate the uh, objective function and the constraints. So let's try to do that first. So area has to be maximized. So f of x is nothing but area, that is equal to length into breadth. And the constraint is perimeter, that is 2L plus 2B is equal to 20. So we have f of x and g of x. Now just follow the same steps and try to find the answer. Okay. All right, let's look at the complete solution. So first we have to um, apply this condition. So what it is going to give? So we have BL is equal to minus lambda into 2 and 2. So we will get B is equal to L, right? So now we substitute this in our constraint. So what are we going to get? For L is equal to 20 or L is equal to 5 and B is equal to 5. So finally, the area is nothing but 5 into 5, which will be equal to 25. All right. And one more problem. So here the constraint is the circle, and the objective function has been not explicitly mentioned in the question, but you will have to formulate it. That is, the distance function has to be written as the objective function. So let's write the distance function first. So we know the distance function is nothing but root of x1 minus x2 whole square plus y1 minus y2 whole square. So this is the distance function, or to find the distance between 2 points x1 y1 and x2 y2. And now we have been given 1 point, that is 1 2. So let us substitute that. So our function will be x1 minus 1 whole square plus y1 minus 2 whole square. But we know this is what we have to maximize. So maximize or minimize. So we have to find both the closest and farthest point from the 1 2. So let's see how we can write this. So even if we take the square root of this function, our objective will not change. So this whatever inside the square root is what we need to finally find the solution. So we can write our function f of x1 x1. Let's call xy. So not x1 x y1. Xy is equal to x minus 1 whole square plus y minus 2 whole square. Now our constraint is the circle that is given, that is x2 x square plus y square is equal to 80. So now let's if we draw this circle, so how it will look. So if you draw the circle, so this is the 0 point, then this will be the point. How much it will be? Root 80. So this will be root 80. Here also we'll have root 80. Similarly, minus root 80, then minus root 80. Then we'll have our point 1 2 somewhere here. So we'll have 1, let's say 2. So this is 1 2. Now what we need to find is we need to find the closest and the farthest point on the circle. So if we draw some line through here, so this will be the closest point and this will be the farthest point. So these 2 points are the points that we need to find by this optimization problem. So just follow the same steps, that is delta f is equal to minus lambda into delta g. So if we write that, what are we going to get? So we have 2x minus 1, then we have 2y minus 2. That is coming from our objective function. Now we have to write the minus lambda into where we have, so this is our constraint. So it will be 2x and 2y. Now we have to solve this problem. So here is a solution. So from the equations we get x1 minus, so we had 2x minus 1 equal to minus lambda into 2x. So on rearranging we get x minus 1 by x is equal to minus lambda, and similarly on rearranging the y we get y minus 2 by y is equal to minus lambda. Now what we need to do is we have to combine our three equations, that is the first equation, second equation, and the constraint equation to solve the x and y. So from if we solve just to combine these two equations. So we are going to get x minus 1 by x is equal to y minus 2 by y. So from here, we can get y is equal to 2x. And now we substitute the same in the equation x squared plus y squared is equal to 80. Finally, if we solve that, we are going to get x is equal to plus or minus 4. And the corresponding, so we have x is equal to plus or minus 4, then y is equal to 2x, so which gives this plus or minus 8. So from this equation, we found 2 points, that is xy is equal to, one is 4, 8, the other one is minus 4, minus 8. So from the figure itself, we can get to know that 4, 8 is the closest point and minus 4, minus 8 is the farthest point. Okay, one more question. If you want to try, I will wait, or we'll just move to the solution. So here is the solution for the problem. So first we have to again follow the same steps. That is, we have to find the gradient of the objective and the constraints. Then use the Lagrangian multiplier. So if you do that, in here we can see that it has three variables in the constraint. So we have to solve. We have to find the derivative with respect to three variables. And straightforward, we get y is equal to 0. And from these two equations, we get x is equal to z. Now, if we substitute the same in our constraint equation, we are going to finally end up with the solution. That is x is equal to plus or minus root 1 by 2. And we have two solutions, that is corresponding to x is equal to z. That will be the same, x and z will be the same, and y is equal to 0. So one will be the point that is maximizing the solution, and one will be the point that is minimizing the solution. So some questions, please try to answer. Am I not audible or something? Is something wrong with the video? Or is the screen not visible? I am getting no
Yes,
response
audible.
from anyone.
Audible, audible.
Okay, fine. So please try to answer these two questions. So
So the first question is it C?
yeah, first question is C. And for the second one,
D.
which one?
D. Option fourth, D.
Okay, fine. So it's just a theory question. So it's straightforward. So this is also kind of straightforward question. So, which is an equality constraint in a linear programming problem shown below. Option B is the answer. It only that one has the equality constraint. Okay, so try to answer this one question. So, and after that, we'll move towards another inequality constraint problems. So if you can please, so if you solve this problem, well, like we can close the equality constraint optimization, and we can move to the inequality constraint optimization problems. So you can try up to 645 and give me the answer.
So can you show the third question again?
Which question?
Third one.
This one. This question.
Yes, sir. Thank you.
So please try to solve this question by 645. You can give me the answer. So hi, anybody has the answer? Did anyone try, or shall I move and show the solution?
Sir, is it C?
Hello?
Sir, is it C?
Yeah, C is the correct answer. So first we have to apply the condition. So we get the two equations combined with the constant equation. We are going to get 2.5 for x as well as for y. So now we will move towards inequality constraint optimization. So until now, what we have seen is the point has to lie on the line. But when it is inequality constraint optimization, it is not necessary that the point has to lie exactly on the line. All right, so yeah, I think these two figures are so let's say so we have two regions here. So one is this red region and the other one is this green region. So one region denotes one side of the line. So if you look at one way to easily see which region belongs to which side. So what we need to do is, so we know 0, 0 is somewhere here. So 0, 0 is somewhere here. So just put that 0, 0 into our equation. So if we put 0, 0 into our equation, then what we are going to get is 3 into 0 plus 2 into 0, that is equal to 0. So 0 is less than or equal to 12. So this is true. So in such cases, our feasible region will be that region with 0. So the feasible region which belongs to this condition is the red region. So this arrow marks are not correct. So this is not correct. So this is the feasible region for this constraint. Similarly, if we put 0, 0 here, so we get 0 is greater than or equal to 12, which means 0 does not belongs to the feasible region, 0, 0 point. So in this case, the feasible region will be this yellow region. So the feasible region is going to be this yellow region. So now any point in this feasible region can be a solution to our problem. So if you look at this condition, so one minute, let me just try to All right, so okay. So here, if you see now, since in this case, this is the feasible region that we have, our problem almost is equal to unconstrained optimization problem, because our solution for the unconstrained and the constrained optimization will be the same. That is, it will be at this point 0, 0. Whereas in case of this problem, since the feasible region is somewhere here, the minimum will be this point, which should be equal to the equality constraint problem. So if it was maximization problem, then it will be somewhere in the infinity. But in this case, since it is a minimization problem, the point lies on this line. So it will be equal to the equality constraint problem. So now let us see how we can solve these kind of problems. For that, again, one more example. So here the problem is to minimize 2x1 square plus 4x2 square. So that is the objective function. And we have two inequality constraints, not two, three inequality constraints. So we'll have x1 equal to 1 line, that is this line, x1 equal to 1. And if we put 0 here, so x1 is less than 0. So the region will be somewhere to this side. Now, again, in this also, if we put 0, 0, so 0, 0 is somewhere here, right? 0, 0. So if you look at this line, that is 3x1 plus 2x2, this line, so 3x1 plus 2x2 equal to 12. And if you put 0, 0, 0, 0 is on the right side. So this region. And for the last line, that is 2x1 plus 5x2 greater than or equal to 10. So this is the line 2x1 plus 5x2 equal to 10. And if you put 0, 0 in that equation, it is not going to satisfy. That is 0 less than or equal to 10. This is wrong. So the region is the region where we don't have the 0. So it will be pointing towards that side. So the common region is the regions denoted by this side, then the upside, and the down. So this is the feasible region. So from this feasible region, whichever points gives the minimum value for the objective function will be the solution for this problem. Now let's see how we can solve that problem using equations. So we have again, we will be using the Lagrangian. So here we have the Lagrangian equation that we write like, so how we write is Lagrangian equation is equal to, first we will write the function plus mu I gi x. So it is nothing but g's are the constraints, inequality constraints, and mu is the Lagrangian multiplier. But one thing to note is that we have to convert all the g's into standard form. What is the standard form? So here we can see that here we have in the A equation, we have something here, then it is less than or equal to some set 12. Whereas in B equation, it is greater than or equal to 10. So what we do is we will convert everything into the same form. So let's say we'll convert everything into less than or equal to 0 form. So how we can convert the A equation? So A equation will be nothing but 3x1 plus 2x2 minus 12 is less than or equal to 0. Now the B equation, how we can convert? So the B equation, we can convert it by 10 minus 2x1 minus 5x2 is less than or equal to 0. and the C equation is x1 minus 1 is less than or equal to 0. So this is the standard form of G equation, that is constraint equation. And now we put it or substitute that in the Lagrangian equation. So if you substitute that, so here we have the f of x, and this is the A equation, then we have the B equation and C equation. And now what we do is we take the gradient with respect to each of the variable. Here we have x1, x2, mu1, mu2, and mu3. All right, so we have to first take gradient with respect to x1, then we take with respect to x2, then we have to take so if you do that, we get equations, and finally we can solve these equations. So if you have doubts, please ask now how to form the Lagrangian and how to see the first order KKT conditions. All right, let's see how we will solve the problem. So in the last problem, we had three constraints, right? So we had, from the equation, we know we had three lines. So if all the constraints are active, so let's say in our last question, we had something like one line here, and one line here, and this was our feasible region. So let's say all the constraints are active. So all the constraints are active in the sense all the inequality constraints are equal to equality constraints. That is, we had Gi is less than or equal to 0, which we have converted into this form. But let's say if one constraint, so let's say the first constraint G1 is active in the sense G1 has to be equal to 0. Or the second constraint G2 is as active, has to be equal to 0, and G3 has to be equal to 0. So if this is satisfied, we say that all the constraints are active. So if you look at our solution space, there is no point such that which is common to these three lines. So if our lines were like this, so if we had a common point to all the three lines, we could consider the situation where all the constraints were active. But whereas in this case, these two have a common point. So let's say these two have a common point here. So this constraint and this constraint can be active, or these two can be active. Whereas here we have one more point, which is common to this constraint and this constraint. But it is outside the solution zone. So it is also not a feasible solution. So let's see how we will find the solution. So first, all constraints being active, it is an infeasible solution. So it is not. So that is, equations do not have a bad solution. That is, there is no common point to all the three equations. Now we are keeping. So let's write the constraints also. So this one is 3. So let's see which is which. So we have three constraints. So this one is 3x1 plus 2x2 less than or equal to 12. Second one is 2x1 plus 5x2 greater than or equal to 10. Then this is x1 less than or equal to 1. Now we are keeping these two constraints active. That is this line and this line. And that have a solution, right? Because we have a common point here. But the problem is x1 less than 1. X1 has to be less than 1. That is not satisfied. That is here, if you see x1 is 3.63. That is not satisfied. So the third constraint, even though it is not active, but we have to get it satisfied. That is x1 has to be less than or equal to 1. So x1 is not satisfied. So that is not a possible solution. Now we are keeping the first constraint, that is this constraint, and the x equal to 1 line active. Then we have a solution, that is x is equal to 1 and x2 is equal to 4.5. Now if you find mu from this, we get mu1 is less than 0. So here the conditions are mu, all the Lagrange multiplier has to be greater than or equal to 0. So if you solve these equations, we will find that one of the Lagrange multiplier is less than 0. So that is also not a possible solution. Now we move to the next point, that is the active constraints are this line and this line. So in this case, we'll have these two as active constraints, and we have a solution 1 and 1.6. And again, we can see that all constraints and KKT conditions are satisfied because mu1, mu2, and mu3 are greater than or equal to 0. But still, we have to see what other possible solutions also. Now we're keeping two conditions are inactive. So only checking this area, and we see that again we have x1 less than 1 is not satisfied in this condition also. Then if we keep only the second constraint active, again we get the violation, that is of the third constraint, that is x1 less than or equal to 1. Similarly, for the other constraints, if we keep active, we have another problem. And if you don't keep any of them active, so the point does not lie on any of these lines. And if you find the solution, again, we are going to get n violation of the constraint. So we have to see all the constraints, that is KKT condition has to be satisfied. If that is satisfied, we get the solution. So these are the different cases that we saw now. So first one is all the three lines has to intersect at a single point, that is all the constraints are active. So that is not going to happen, since as we can see from the figure. And in the second case, these two lines were active, and this was the solution that we found. But it is outside the, or this is our active region, so it is also not satisfying. And in the third case, we found this point. So these are the solution. If we keep these two are the active constraints, but we got the Lagrange multiplier to be less than 1, less than 0. So that is also not an optimal solution. Whereas in the fourth case, when we took these two as the active constraints, we got our optimal solution. And other cases we just took. So what was case 5? Yeah. So case 5 was only this was the active constraint. So we got some solution here. So that was violating the feasible region. Similarly, for the second case, we got a solution here, which with this single constraint being active. which was also violating the feasible region condition. And in third case or seventh case, we took only one active constraint. Then we got the solution somewhere here. So if you see this solution, it's also kind of tangent to the function curve. So we got a solution here, but our feasible region is this region. So it was also violating the feasible region. And finally, if it don't consider any of the constraints, this is the solution that we got, and it was also violating the feasible region condition. So this is how we find the solution for the multivariate inequality optimization problem. So we have some questions. So this is the answer is B. So the second question, please try to answer.
C.
Yeah, C is the correct answer. All right, then we have two more questions.
Yes, sir.
For the first question, A is the answer, and for the second question, the answer is D. So one last question. So it's like how we are forming the Lagrangian functions. So here, what are the constraints we have? So we have G1 is equal to X plus Y equal to 9. Then G2 is 2x minus 9y less than or equal to 1. Then G3 is xy plus 3 greater than or equal to 3. So we have to convert everything into standard form. So this is an equality constraint. So there is no need to convert. So this one we can write it as 2x minus 9y minus 1 less than or equal to 0. This we can write as 3 minus xy minus 3 less than or equal to 0. So now if you write the Lagrangian, so we have the function, objective function here. Then this is the equality constraint, which is given using lambda, we can write. Then for inequality constraints, we use the Lagrangian multiplier, mu1 and mu2, and we have to insert these two equations. Sorry, which is the correct answer? Actually, no answer is correct. I think. This is not, this has to be 3 minus xy minus x. Sorry for the typo. I will correct the solution and send it. Sorry for the mistake. So the correct answer has to be 3 minus xy minus x. All right. Okay, so now we'll look at some of the questions. Okay, so yeah, try to. We'll be looking just at the questions and answers.
The option C.
So the first question is which option C, which means not true, right? So option C means this one. Okay. So that's the correct answer. Now the second question.
So false.
That's false. Okay.
So is it B?
Which one?
Second option B.
Yeah, B is the correct answer. Yeah. So the next question. So this is an unconstrained multivariate optimization. So it is asking the necessary second order condition for the minimization of the function.
So option B.
Yes, option B is the answer. Yes. And yeah. So this is also unconstrained optimization problem. So You will have to solve it. So we have to find the delta f. So that will be equal to 2x1 minus 2 and 8x2 plus 8. Now equate that to 0, we get x1 is equal to 1 and x2 is equal to minus 1. So the option B will be the correct. And now try to find the Hessian matrix of the same question. So here is the function. Now try to find the Hessian and try to find the eigenvalue. So I will write the function. So I will write the function again. X1 square plus 4x2 square minus 2x1 plus 8x2. Find the, this one we have already found, 2x1 minus 2 and 8x2 plus 8. Now we have to find the Hessian.
Is
So
it
Hessian will
option
be
C?
nothing but, yeah, please go on.
Option C, sir.
Yeah, option C is the correct answer. So we have 2 and 8. Yeah, option C, 2 and 8. Okay, so it will be 2008. Now we find the h minus lambda I and find the derivative. We get 2 minus lambda 0, 8 minus lambda, which we get 0. We get 2 minus lambda into 8 minus lambda is equal to 0, which gives lambda is equal to 2 or 8. So what will be the minimum value? So we have to just, we have already found x1, x2, just we have to substitute that to the equation. Is x1 square plus 4x2 square minus 2x1 plus 8x2. So x1 is equal to 1 and x2 is equal to minus 1. So it will be 1 plus 4 minus 2 minus 8. It will be equal to minus 5. Okay, so minus 5 is the answer. Now let us see what will be the answer of the function if we add a constraint to that. Again, our function is x1 square plus 4x2 square minus 2x1 plus 8x2. And we have a constraint here. So try to answer it. So we need to find. Let's use the Lagrangian way, right? So since we have already done that, so we have Lagrangian is equal to f of x plus lambda into g of x. So if you write that, we get x1 square plus 4x2 square minus 2x1 plus 8x2 plus lambda into x1 plus 2x2 minus 7. Now let's take the derivative. So if you take the derivative, we get dou L by dou x1 equal to 0 implies 2x1 minus 2 plus lambda equal to 0. Then dou L by dou x2 is equal to 0 implies 8x2 plus 8 plus 2 lambda is equal to 0. Now using these equations and the constraint that is, so let's say we take the derivative with respect to lambda also and equal to 0 implies we get x1 plus 2x2 minus 7 is equal to 0. So if you look at these equations, this is nothing but, so if you write these equations in the form minus lambda g, we get 2x1 minus 2, then we have 8x2 minus 8 plus 8, that is equal to minus lambda into 1 and 2. So that is nothing but this we have here. And if you take this into other side, we get minus lambda into 1 and 2. It's the same that we have already studied, that is of the form delta f and minus lambda into delta g. And this is the final constraint that we have. So by combining three equations, we will able to find the solution. So from here, if you try to find the solution, finally we'll end up with the answer 27. We can please try it. Now another similar problem, constraint optimization with equality constraint. So here we get three equations. That will be minus 2x and plus minus 2x is equal to minus lambda, and minus 2y is equal to minus 3 lambda, right? So if we solve that, we get, so let's say lambda is equal to, from here we get lambda is equal to 2x. So we substitute that here, 2y is equal to 6x, or y is equal to 3x, right? Okay, and now we have to substitute that. Substitute that here. So we get x plus 9y is equal to 10, or x is equal to 1, and y is equal to 3. So the maximum value will be equal to 49 minus 1 minus 9, that will be equal to 39. So this question, no, yeah. Consider an optimization problem. So what will be the Lagrangian? So we'll have the f of x. Then we have to convert everything into the standard form. F of x is common everywhere. So this is in the standard form, whereas this is not in the standard form. Now we have to see which all are having. So this is not an option. And this is in the standard form. This is not, even though this is in standard form, this is not standard form. This is standard form, this is not, this is, and this is. So the correct option is the first one. Now you have some practice questions. So should we do? So considering the objective function, that is maximize f of x is equal to xy, subject to x plus y square is less than or equal to 2, and xy is greater than or equal to 0. The Lagrangian function is given by xy minus mu1 minus x minus y square plus 2 minus mu2 into x and minus mu3 into y. So which of the following is not an apt representation of the constraint? So that is the question. So here, if you see this, you might feel this is not in a standard form. But if you write like xy plus y mu1, and if you take the negative sign inside, you can see that it will be nothing but x plus y square minus 2. Again, here we have mu2 into plus mu2 into minus x and plus mu3 into minus y. So this is one of the constraint. Then the other constraint are x is greater than or equal to 0 and y is greater than or equal to 0. So here we have to convert that into the standard form, what we need to do is, let's take the x to the other side and y to the other side. So it will be x less than or equal to minus x less than or equal to 0 and minus y less than or equal to 0. So one of the not apt representation of the constraint is the option B. So this is also a part of the concept. Now again, the same question. So let's try to see how we can solve this. So when all the constraints are active, okay, so we might have to go back to our KKT condition or that slide. So what we have said on that KKT condition is, so let's say we have the Lagrangian, that is f of x plus mu igi of x. Then the conditions that has to be satisfied was, that is delta L has to be equal to 0. Then mu I converting all the inequality constraints into equality constraints. So let's say gi x has to be equal to 0. How can this be equal to 0? Okay, so if a constraint is active, so if a constraint, if g of I is active, so let's say this is one of the constraint less than or equal to 1. So if this is active, this constraint is active, it takes the form g plus y is equal to 1. Okay. So what we can say is that mu I into x plus y minus 1 has to be equal to 0. So this is needed for the condition, and mu I has to be greater than or equal to 0. So for all equal, if a condition is active, this has to be the condition, or all the inequality constraints has to satisfy this condition. So if a condition is active, then this is satisfied. Whatever inside the bracket is satisfied, so that this has to be equal to 0. So that mu I can take any values greater than or equal to 0. Whereas if a constraint is not active, then this equality constraint is not satisfied. So that in order to satisfy this condition, that is mu I gi equal to 0, this is not equal to 0. So mu I has to be equal to 0. So if all the constraints are inactive, which means none of the gi is, or none of the inequality constraints are converted to equality constraints, then all the mu i's has to be equal to 0. So in this case, the correct option will be mu1 equal to mu2 equal to mu3 equal to 0. So next question, we have the function. So this is a normal and constraint optimization. So you guys can so just show the solution. So we have to just take the derivative of both the sides, both the variables, and we have to equate to 0. So this is similar to what we have already done in the class today. So we need to find the distance function and we have to find the solution. So yeah, first we have to define the objective function. Then we have the constraint here and the multivariate objective optimization steps we have to follow. So we get 3 equations with the Lagrangian and we can find the solution. Now the next one is a function is defined and we have the constraint also. So let's try to do this one. So L can be written as f of x plus lambda into now we have delta L equal to dou L by dou x, dou L by dou y, then dou L by lambda. So we get 10 minus lambda plus lambda. Then we have 5 plus lambda, 5 plus 10y lambda, and we have one more equation, right? So we get 5x plus 5y square minus 44. Only 5 lambda. Okay. So we can substitute for lambda. So we have to get this to 0. So if you find the lambda from the first equation, we get lambda is equal to 2. Then from second equation, we get y is equal to 20.5. Y will be equal to 0.25, 0.25. And then we have from the last equation, we can find x. That will be approximately equal to 8.73. So the option A is the correct answer. We have a few more questions. So I will show the solution. So here the profit is given by revenue minus total cost. So that we get the objective function. And then we can just take the derivative and find the answer. So this is a theory question. So we have n variables and one equality constraint. So if you write the Lagrangian and take the derivative with respect to n variables, we have n equations, and in addition to that, we have the Lagrangian multiplier also. So if you take the derivative with respect to Lagrangian multiplier, it will give the inequality or the equality constant itself as the equation. So we have n plus 1 equations, and considering Lagrangian also as an equation or as a variable, we'll have n plus 1 variables also. So option B will be the correct answer. Okay, so these questions I don't want to solve in the class. I will post it in the drive, so you can solve those questions there. Okay, so that's it for today's class. So if you have any doubt, you can ask now, or we will end today's section.
Sir, can you please show the previous question?
This one.
Okay, sir.
So I will show the other questions also if you want to take the screenshot. So this is one question. And now this is the next question. All right, so see you next week. So I will end this section here today. Thank you for joining.
Thank you,
Thank you
sir.
so much, sir.